Hey physicists, this screencast will cover some of the problems in our force equals mass times acceleration topic 2 cycle 2 problem set. I'll use our standard 5-step problem solving technique, drawing a picture, listing what it is I'm trying to find, list what I'm given, the relationships or equations that might be used for this, and solve, and then my final check on the smell test. Go ahead and draw a picture. So let's take a look. Engineers at the Johnson Space Center must determine the net force, net force is what we're looking for a rocket to achieve an acceleration of 70 meters per second squared, and the mass of the rocket is 45,000 kilograms. How much net force must the rocket engine develop? So here's my picture. I have my rocket here accelerating to the right, rocket fuel coming out the back here. Okay. What are we trying to find? We're trying to find our net force, and we're given that the acceleration is, or required, is 70 meters per second squared, and we also know that the mass of the rocket is 45,000 kilograms. Relationships. Hey, do we have an equation that relates those things that we're looking for, F net, and those things that were given, acceleration and mass? Yes, we do. In this case, we know that net forces is equal to mass times acceleration. Let's go ahead and solve that. Our net force, we're going to be particular about units now. 45,000 kilograms times our acceleration, 70 meters per second squared. What does that equal? I multiply these together and I get 3,150,000 kilogram meters per second squared. Remember our dimensional analysis, we know that kilogram meter per second squared is a Newton, so 3,150,000 newtons. Is this reasonable? Well, I took a quick look on the internet, and the Saturn V rocket, which was used to launch the first men to the moon, developed about 35 million, sorry about this, newtons of thrust, and we're looking for an engine that is about 1/10 that. So, yep, that checks out. Next, we'll look at number 5. This one's looking for mass, and we can see the problem. What is the mass of a falling rock if it produces a force of 147 newtons with an acceleration of 10 meters per second squared? And let's see, we'll have our, maybe our rock here, it's falling. Here's me, ouch. About to hit my head. Okay, and what are we trying to find? We're trying to find the mass of the rock, and we're given both the force of 147 newtons, and we're given the acceleration of 10 meters per second squared. Perhaps that's how much I'm being pushed on or something. Relationship. Okay, we're looking for our mass. Okay, previously we know that, let's see, acceleration is force net divided by mass. Let me rearrange that. I know that mass is equal to net force divided by acceleration. If the algebraic manipulation go from this to this is a bit confusing, stop and see me. Okay, let's see. Let's solve this. We now know that m is equal to our net force divided by our acceleration. Let's go ahead and put in numbers. Our net force is 147 newtons. Our acceleration is 10 meters per second squared. Let's go ahead and find that. What that is, 14.7, and I have newtons per meter, or meter per second squared. You might say, hey, this doesn't really make sense. Let's go in and put in the other units we have for Newton from the previous problem. Remember, a Newton is the same as a kilogram meter per second squared. We'll divide that by meters per second squared. Now for 14.7, we see that our meters per second squared cancel in both those, so we do have something that looks reasonable. 14.7 kilograms. So the mass of our rock is 14.7 kilograms. Okay, we're now looking at number 7, and this one we're looking for acceleration. What is the acceleration of a softball? Here's a softball with a mass of 0.5 kilograms, and it hits the catcher's glove with a force of 25 newtons. Now the catcher's glove is a little more round, so I had to make it a little more round there. Okay, so what we're trying to find is acceleration. Okay, and we're given a mass of 0.5 kilograms. We're also given a force. We'll assume that this is the net force, the only force that's mentioned in the horizontal direction, 25 newtons. Let's see if we can find that relationship. The one we've been dealing with most commonly is that acceleration is equal to our net force divided by our mass. Let's go ahead and solve that. So if we have A is equal to our net force, 25 newtons, our mass is 0.5 kilograms, we can see that we have 50 newtons per kilogram. Let's see what that works out to be. Remember, our newton is a kilogram meter per second squared, and we'll divide that by the kilograms we had here. Cancel, cancel. So we do get, our units are correct, 50 meters per second squared. We'll assume the catcher is trying to slow that down. The softball pitch is at around 20 to 25 meters per second, so it would take about half a second for this to slow down. Is that reasonable? Maybe a little bit long, but it does pass the smell test. Okay. This next problem is going to be a little more challenging, so let's take a look at it. A catapult is used a lot in an F-18 airplane horizontally from the flight deck of an aircraft carrier. Here's our aircraft carrier, here's our aircraft. The plane's takeoff speed is 80 meters per second. That's going to be important. If it doesn't go fast enough, the plane doesn't fly. The F-14, whoop, that should be F-18. Sorry about that. We updated this to the newer aircraft. It starts from rest. The plane accelerates in 2 seconds and has a mass of 15,000 kilograms. What is the net force that gets the F-18 in the air? So I've drawn my picture here. We have the airplane on the deck of the aircraft carrier. Starts from rest and it's being shot off the end of the aircraft carrier. We know that by the time it gets to the end of the aircraft carrier, it has to be going 80 meters per second at least, and it only has 2 seconds to get there. So what are we trying to find? We're trying to find the net force. The net force. What are we given? We're given that that the mass is 15,000 kilograms. Now the other thing is we're not given an acceleration, but we are given a final velocity of 80 meters per second. We also see that it's starting from rest, so we know we have a starting velocity of 0 meters per second, and we're given a time. That might be helpful. And time is equal to 2 seconds. Let's see our relationships. Okay, so the most obvious one is that our net force is equal to mass times acceleration, but I'm not given acceleration directly. But I do know that acceleration is my change of velocity over my time. Okay, and given the values that we've got here, I'll have to use this relationship to figure out my acceleration. Let's go ahead and solve this. First, let's go and solve for acceleration. That's going to be, our acceleration is going to be 80 meters per second minus our 0 meters per second over, and how long did it take? 2 seconds. Let's see, our acceleration here is going to be 40 meters per second squared. Pretty quick. We'll soon learn that that's a value of about 4 G's. Probably heard that term before. But what we're actually being asked for is the net force is equal to our mass, 15,000 kilograms, times our second squared. What does that work out to be? Works out to a force of 600,000 newtons. Quick check on the internet. I couldn't quite find the force that an aircraft is launched with, but I did find what they call g-force, or the acceleration, is between 3 and 5 g's. So this value that we have here is pretty reasonable. Next problem looking at is number 14. This one will be a little bit interesting. We've got multiple forces and we're looking for acceleration. So let's go ahead through our 5-step problem solving. Okay, so we have a rightward normal force. Maybe someone's pushing it here or something like that. Oops. They're pushing it to the right with a force of 300 newtons. The frictional force between the crate and the floor is 200 newtons. We know that will oppose the motion, so we know that that's that direction of 200 newtons. And it's asking to determine the acceleration of the crate. So what we're trying to find is acceleration. And what are we given? We're given a force to the right is 300 newtons. The frictional force, which is to the left, is 200 newtons. And we know that mass is 25 kilograms. What's our relationship? Well, we're looking for acceleration, and we know the acceleration is equal to, this will be an important part, F net divided by mass. Let's go ahead and solve that. So our acceleration is equal to our F net divided by mass. F net is going to be, let's see, we have 300 newtons to the right. And I'll call the right the positive direction. So we have 300 newtons, and then we have 200 newtons opposing that. So to the left I'll call the negative direction. So minus 200 newtons over 25 kilograms. So we have, a net force of 100 newtons to the right divided by 25 kilograms, and our 100 newtons divided by 25 kilograms is going to be equal to 4 newtons per kilogram. We saw earlier that that's the same as 4 meters per second squared to the right. Is that reasonable? Let's see, gravity, things that fall at about 10 meters per second squared. Could we push about half, with about half the acceleration of that? Yeah, probably reasonable. So our examples covered, number 1 covered finding force given mass and acceleration. Number 5 covered finding mass given force and acceleration. Number 7 covered finding acceleration given force and mass. Number 12 covered the idea of finding force and finding acceleration from 2 velocity datas, and data is plural. And number 14 covered determining acceleration from a net force. This should give you an example of each of the types of problems in this set 1 through 17.